So thank you very much. Today, Alessandra Pizzuti is here. Alessandra is a PhD candidate from Maastricht, where she was working with, or is working with Rainer Goebel in his company, Brain Innovation. She is part of this Marie Curie European Union training program, the grant. And she will introduce herself in more detail, I think, on the first slide. What I want to say, though, is that this is being recorded. And I also want to mention that there will be group lunches today at 12:15 and tomorrow 12:15 in the 3T conference room. Everybody's welcome. Also tonight, we are going to go out for Indian food in Bethesda if anybody wants to join. Thank you.
All right. So, good morning, everyone. So my name is Alessandra. Thanks a lot for inviting me here and giving me the possibility to talk a bit about what I've been working on in the last year. And thank Renzo for the introduction. So the title of my talk today is Zooming into the Human Visual System using fMRI at 7 Tesla, from whole brain networks to cortical layers and others. So before I will get started with it, I just quickly introduce myself for who doesn't know me. So I'm a biomedical engineer by education. I graduated in 2019 in University La Sapienza in Rome, in Italy. While I was studying, I already started a research position for a couple of years in a clinical neurorehabilitation center in Rome that's called Fondazione Santa Lucia, under the supervision of Viviana Betti. This is the center, and that's me, trying to collect some data with my colleagues. And I was interested in understanding the kinematic of the ends and how this correlates with some brain activity, in particular with high density EEG and MEG data. It was a very nice period, and we have a few publications out of it that if you're curious, you can check out here also to learn more about the project. After that, I decided to apply for a PhD position following what I was always interested in. So being able to use a high field MRI scanner for brain imaging. That was unfortunately not possible because of the lack of scanners of high field in Italy. So I had to move to the Netherlands, and I was lucky enough to get into the PhD together with Rainer Goebel, that is my supervisor, with 4 years in his company, Brain Innovation, that's basically developed some software to analyze imaging data, fMRI in particular, but not only that. And as Renzo mentioned, I was hired as an early stage researcher in a Marie Curie training grant called European School of Network Neuroscience. It means that there are like 15 universities or entities over Europe that they will try to study the brain, but with different methods and technology and also species. So that's me. During the whole 4 years, I use all the time high resolution fMRI, 7 Tesla, and I started to study like the visual system. Okay, if you want to know more about the grant and so on, there is a link down here. Okay, so during this presentation, I decided to give you a bit of an overview of what project that I've been working on during my PhD, where the overarching goal is to try to study the human visual perception, in particular the visual motion perception. And we will go through a small journey across scales. So we will start from the macroscopic perspective, and we will try to use some whole brain effective connectivity modeling approach to derive some hierarchical measure that can help us differentiating different visual states. Then we will go a bit deeper in the mesoscale, so with a voxel resolution that is below a millimeter. And we will first focus on HMT plus or V5, that is a motion sensitive area, and we looked up to some tuning property of this area with ASO. And then we will touch upon a study that tried to understand different laminar connectivity between V1 and HMT plus in 2 different conditions, feedback and a feed-forward condition. And finally, we will even go a bit more deeper and try to look at the macroscale with the long-standing goal of advancing our understanding between the structure to function coupling. So I've been using some microscopy data from human and try to correlate with some mesoscopic layer fMRI data, and we will still look at the visual system. So V1, V2, V3, and HMT+. So let's get started with the first project. So I mentioned that we will be looking at different visual brain states. So this is the first one. This is a visual illusion called bistable motion quartet stimulus. While I'm talking, I will ask you to look at the screen, in particular to these red dots here in the center for a few seconds, and try to respond in your mind to where do you see the square moving. If they are moving left to right, so along an horizontal motion, or if they are moving up to down in a vertical way. And the illusion consists that there is actually not motion happening in the stimulus itself. There are only like flickering squares, but it's your brain that interpolates information and allow you to perceive one direction of motion or the other one. And this perception, it actually should switch over time. So I hope that you are getting a bit into the illusion and see that all of a sudden you are now perceiving the opposite. So the second brain state is the one elicited by looking at the most boring physical motion condition. Here, there is no ambiguity. So everyone will agree that these squares are physically moving left to right and then up to down. So, and the last state that we incorporate in this study is the resting state. So where participants just look at the fixation process. Okay, to do that, so we conduct like a data collection at 7 Tesla from 9 healthy participants, only one session of 2 hours in Maastricht. And we had like a spatial resolution 1.8 isotropic millimeter and reasonable height ER, 1 second. We use 2D EPI gradient evolved sequence, standard, I would say, and we collect 4 runs of ambiguous motion where the participant is lying in the scanner. The design looks like this. He will be presented to 80 seconds of the same illusion, and during that time, he will press a button to indicate when he's perceiving one state and then switching to the other states. So this is a self-reported paradigm. And then it will be alternated with a rest condition where all the 4 inducers or squares are flickering together. And this is then repeated 6 times. Then we collect 2 runs for the physical motion, where, as I said, there is no ambiguity and the states alternate in a very ordered fashion every 10 seconds. And then 1 final run of about 10 minutes with resting state and anatomical structure imaging with conventional MP2H. Okay. All right. So I said that in this project, we will look at the brain as a network, and we will try to understand it from the perspective of effective connectivity. And this is a concept that is well known in the literature, and there are many, many methods that you can use to tackle this problem, like from simple functional connectivity to DCM, to Granger causality, and so on. For this study, I really want to learn a new technique that incorporates a different and try to claim to extract a different information from the time series. That is the concept of irreversibility. It's a theory that comes directly straight from the physical field, so the second law of thermodynamics, and it claims to characterize the whole brain as an irreversible system. What does it mean? That if you have a system that has to go from A to B and then to B to A, this movement will produce an entropy that is different from 0. And by entropy, it means works and it means energy. So this concept of irreversibility will be used and extrapolated from the empirical data as a measure of directionality of coupling of 2 brain areas. And we can extend this to every couple of areas that we are parcellating our brain. And we will apply this to the 3 states that I mentioned before: ambiguous motion condition, the physical, and the resting state. Okay, so this concept of irreversibility, it jumped into a modeling framework that was already being established by many years from Gustavo Deco's group in Spain. It basically describe each node of your brain as a Stewart-Landau oscillator. And you start with the structural empirical connectivity matrix that come from diffusion data, where in each entry of the matrix, you can say if the two areas are anatomically coupled or not. With this, then you start generating your time series for each node and their coupling. And thus, this empirical structural connectivity matrix at the step 0 will be updated over time. And this update will take in input the information coming from the real-time series. That is this empirical irreversibility and a matrix of functional connectivity. So the empirical irreversibility matrix look like the basically functional connectivity matrix with the same dimension. And but the characteristic is that if you take an entry of the matrix, this will not only tell you that the two areas are actually synchronous, so coupled together, but also it will give you hopefully an information about the directionality. So which one is driving more the other one. And it was exciting because this is a very general approach that if it can work, it can be applied to any kind of time series. So after this log fitting, then you get out of the model and generative effective connectivity matrix. And as I said, it will give you like the coupling between area, but also the direction. It's important to understand that this process, it claims to give you a mechanicistical explanation from the states that you are observing in the brain. So something that you cannot get directly from the time series. And starting from this, then we will compute extra metrics for brain states. Right, so we jump directly into our results. So we stretch the framework to fit it in our protocol. That was a self-reported like peculiar block design approach that was not yet implemented. So I dealt with this, and we were successfully able to go through all the procedure. These are group results. The first step is to compute this no reversibility matrix for the three states that are indicated here on the x-axis, the ambiguous physical and the rest condition. This is the no reversibility value, and each dot is a subject. From the empirical perspective, we could confirm that the rest condition is actually less no reversible, but the no reversibility goes up in the task. And these are results that they are already published, so we could replicate this property in the brain. So take always into account that no reversibility is related to the concept of asymmetry in the brain. And asymmetry is related to hierarchical organization. So higher is the no reversibility, more symmetric and more hierarchical is the system that you are trying to characterize. Then after the modeling, you get a matrix like this, called generative effective connectivity, that look like symmetric from here, but actually the value, the paired are not the same. And this gives you the information of the directionality. And you get one of these for each subject and for each condition. And after that, we compute this extra two matrix, quantitative matrix, a measure of global asymmetry and a measure of trophic coherence. Global asymmetry as basically a bit more complicated than no reversibility, but it has the same meaning. So how much directional is the network itself? Whereas the global, the trophic coherence is inverted to the asymmetry, so you see the different trend, and is a measure of recurrency. And with this, after the modeling, we could find a significant difference even within the two tasks that are again reported on the x-axis. And we found that ambiguous condition is at the end, as maybe also expected, more complicated and required to the brain to be states that is more hierarchical organized to resolve the ambiguity and that you have a perception differently from what you see in the physical condition. Take into account that the difference between the two states are here measured in a globe scale. So it meaning that I'm considering all the coupling happening in the brain, whereas maybe only few regions might be actually driving this phenomenon. And this is what I try to quantify here. So computing these hierarchical jumps. So after this modeling, then we can even attribute to each node a value of hierarchy. So how it's high in the hierarchical system. And we do this from the physical condition and from the ambiguous one. And then we do a simple subtraction to see where the nodes are going while passing from a state to another one. And if you only consider the 30%, and this is a group result, we could find some region that we were expecting to have this kind of behavior. For instance, V1 is going down in the hierarchy while going to the ambiguous condition, whereas MT is like pushing up. But these are not only two areas that of course are involved. The system is much more complex, so we try to bring it to the extreme and only look to the 5% of these nodes. And we find interesting frontal area that are going up, and we are for now not focusing on the one that goes down. But that's now still a bit ongoing, the interpretation of why this area are the so putative generator of changes in hierarchy. Okay, so with that, I would like to wrap up the first project. So, and what I learned from this is that this computational model that can be very useful to get and offer a mechanistical explanation for different brain states. And they give you a measure, in this case, a quantitative measure of hierarchical information. And also the reason why I got into it, because it's such a general principle, this irreversibility that can be applied to any time series. So we were thinking at the beginning to actually apply to layer time series. And by like modifying the core of the model to initiate a different structure of connectivity, it has to integrate the information of the layers, and we can maybe aim to push it to the layer domain. With that, I'd like to thank my collaborators from Maastricht, Rainer, Judith Peters, and Faruk Kuban, but also the people that asked me in a nice way in Barcelona, Gustavo, Deco, and Irene made this possible. Okay, so with this, I would like now to go a bit down in the scale, and we reach now the mesoscale. And I will introduce the first project that I've been working in my PhD, actually. It's not in chronological order. That was where Renzo was also in Maastricht. And we tried to image the columnar functional organization of human area MT plus to a specific stimuli that we call axis of motion stimuli using Bezo and 7 Tesla. So this study started with a very humble request. We just would like to check the feasibility of studying this tuning property of MT plus that is already well known in the literature, and many bold fMRI studies have reported, but just using Bezo. So we use a conventional stimulus design that consists of dots organized in a circle aperture that they move along one of the 4 axes of motion, so they can go up and down, left to right, or along the 2 diagonal. This is a simple block design protocol, and it's interbuilt with a rest condition that we call flickering, where there are like these dots. They don't move, but they change their intensity so that they give this flickering situation, perception. Then we look at the MT, and we try to see if these tuning properties are actually organized spatially in so-called cortical columns. To do that, we collect data at Tesla from 5 participants, 1 session of 2 hours. We used an adapted sequence that Renzo developed, and with a sub-millimeter resolution, 0.8. We had like a bit longer PR, but was not finished in our case since it was a mapping with a 3D acquisition. And we also use an online localizer for HMT class to be able to place correctly the slab before collecting the data for the main experiment. And finally, like an in-situ range. Okay, so here I'm showing you already directly the result of our study. So these are group results from all the tuning cores that we obtained. So in the first row, we have the bold contrast, because with the Bezo sequence, you get for free 2 kinds of contrast. You have a bold fMRI contrast, but also a CVP-based contrast that is supposed to be more specific to the neuronal activity. and maybe more useful to detect this kind of property. So this was a question. So here I'm showing results for both and for basal. Different shade of colors indicate different way of doing the voxel selection, just for us to be a bit more pedantic. And each subplot indicates the behavior of a group of voxels that we detect being preferentially responding to the condition that is highlighted in green. So for instance, it's horizontal. On the x-axis, we always have the core condition. And then on the y-axis, we have the t-value, so the strength of the response, I would say. And we can observe this characteristic tuning behavior for which in the preferred condition, you have a much higher response versus the non-preferred condition, though it's not zero. And this is very consistent across participants, since this a group result, and across contrast mechanisms. So we could successfully say that we can use basal and we can see the same pattern. However, this was not enough for us because we want to try to give a quantification of how different are these two contrast mechanisms with respect to this property. And that's why we took inspiration from a previous measure of sensitivity and specificity. And this is how we all talk about that. And there are a lot of great work already done that try to quantify how two different contrast mechanisms are globally more specific or to which kind of microstructure, or how much are also sensitive in terms of SNR and so on. What we did here in a novel way, we just extended to each voxel. We want to give like a value to each voxel of them. And this could complement the information that we get from the tuning curves as a map also, and it will allow us to compare the two contrast mechanisms for each voxel, very local. And maybe this can give us also some insight. The computation of the voxel-wise sensitivity and specificity is actually very simple. Like, let's assume here for simplicity that you only have two conditions instead of four, but this is generalizable to n condition. And that you can quantify the response of each voxel to the two stimulus through some weights that can be betas, can be even, whatever. Then we take these weights and we use it as a component of a vector in a vector space. So here, for instance, I'm indicating the vector for two indicative voxels. The sensitivity is just the length of the vector, and it's telling us how strong that voxel is responding to any of the conditions that we are presenting. Whereas the specificity is an indirect way of computing an angular measure, and with respect to the axis that is closer to the winning weights between the two. So in this case, for instance, the blue one is closer to stimulus A, and then we will compute a kind of angular measure to say that this voxel is more specific with respect to the voxel number. And if you repeat this to every voxel in our region of interest, and we look at them as a distribution in a Cartesian axis, so sensitivity on the x and specificity on the y, in an ideal world, we would like to have our voxel up here, very sensitive and very specific to the stimulus. But unfortunately, that's not the case. Neither both does the job, and we saw consistently different distribution, and the bold one across different voxel selections, very robust. In the bold, we can see that there is a tail stretched on the right side that indicate voxels that are very sensitive but not specific, not surprisingly. And for basal, the sensitivity range is cut in half mostly with respect to the bold one, but the range of specificity is stretched to the upper part, meaning that in theory those voxels are more specific. Okay, so saying that, of course, sensitivity and specificity are really related to the microvascular weights behind the two contrast mechanisms. So we could even visualize now why having a map would be useful to highlight vascular structure. For instance, here is an example from one participant. This is a delineation of white and gray meter boundary. And this dark spot that we can see and visualize nicely with just the mean of a T2 star weighted signal indicates a vascular structure. If then we take this piece of the cortex and we flatten, just to be a bit more handy to see at the same time pre-cortical depth, we can see that the dark spot in the flattened domain is only located to the superficial layers. So meaning that is quantitative, be representative of the pile vessel. And not surprisingly, those voxels in terms of functional sensitivity and specificity are super bright, exploding sensitivity, so signal is there a lot in the bold contrast, but their specificity is very low. So the combined information, it sum up at the end to this independent benchmark. And this is, of course, not visible in basal. It's much more mitigated, but not also completely resolved. So it was good for us also to have this. Okay, finally, here we move to the columnarity measure. So then our question was, can we try to quantify how HMT plus is actually columnar, how much columnar volume is inside, that we can extrapolate in a data-driven way from our data. Because for now, we just started with a preference map. So we can associate to each voxel which condition they are maximally preferring. Then, and we couldn't find in the literature a method that was giving us a map that we could scroll and see, okay, this area is more columnar than another one. Therefore, we leveraged the expertise of being able to parameterize fully a piece of the cortex, injecting a coordinate system there. So we can have U, B, and D. They are all orthogonal and they are geodesic defined. And in this weird space, then we create cylindrical kernel that is fully parameterized by a height and a radius. And we basically make use of it as a searchlight. We place this cylinder in every position, in every voxel, and then we ask in how many voxels within this kernel are actually showing the same preference. If all of them, of course, these cylinders span the whole cortical depth. If all of them are showing the same, then we have a full column. So all the columns is responding in the same way. But if only few of them, we can then estimate and quantify a percentage out of it. And this gives us as output what we call the columnarity index map that we can scroll and we can trash in different ways. Since columns are nice to see in the flat space, here I'm showing again in the flat domain that they look like real columns of pillar. And I'm showing you the result for different thresholds of the columnarity index. We start requiring a very low, so only 20% of the data showing the same property. Then we can go to 50% and became even higher. And we show it result for bold and basal, and then how much they agree. Each color here is a preference to one axis of motion. And what we observe is that actually in our data show that we don't have a whole columns. So now it can be for loss of sensitivity or many more reasons. But the highest amount of columnar volume we found for smaller columns that have a columnarity index around 40 to 50%, so half of the data. All right, so as this, I will wrap up this project as well. And our take-home message was, yes, we can definitely use ISO to study tuning selectivity in HMT+. Our data support this. And we hope that the toolkit that we developed, this voxel-wise measure of sensitivity, specificity, and columnarity, could also improve the quantifiability and reproducibility of the fMRI result across different studies that maybe target the same property, but with a different sequence and so on, so that we can compare a little bit more quantitatively. Okay, so then we are moving to the third study, where I promise that we are looking now at the laminar connectivity between two brain regions, so V1 and VT, and not anymore in isolation, in two conditions, feedback and feed forward. What does it mean by that? It means that we use the stimulus that I showed you previously. So the ambiguous stimulus that is a proxy for, we think being a proxy for a feedback condition, because there is no sensory disambiguity. So some of the area might send the feedback to V1 and dictate which of the two conditions we are currently perceiving, versus a more feed-forward driven condition that is the physical motion. There is no ambiguity, the sensory stimulus is there, and we expect information flow going from V1 to HMT plus. So we call back our participant for 2 more sessions, so for a total of 6 hours of scanning. And here we use again sub-millimeter resolution fMRI data, 0.8, slightly longer PR, 2 seconds. And we did decide to use a 2D EPI gradient echo to have a good compromise of coverage, because now we need much more coverage with respect to the previous study. And we also need to be a bit faster in sampling the temporal dynamics, because the way that people switch across states is vary a lot, and no matter how much selection of good participant, also behavioral we did, they still can switch starting from 4 seconds and arrive to up to 20. So that's why we at the end choose to use this sequence. And we collect 6 run for ambiguous motion and 6 run for the physical motion. We did the same trick as before, an online localizer for HMT, and some 2 retinotopic runs for defining the E1 border. Okay, since we are at mesoscale, we can zoom into a bit more the 2 regions of interest, and we propose this study in a very schematic and simplistic way 2 alternative hypotheses of what could potentially happen at the mesoscopic scale. So V1, we know that we can define retinotopic cluster, meaning that we can individuate voxels that are basically in between the 2 inducers in the horizontal patches and the vertical one at the corresponding. And MT plus, we just talked about axis of motion columns, or patch of voxels that preferentially respond to one motion versus the other motion. So we will call it columnar cluster for simplicity. So in hypothesis 1, we were thinking of, let's assume that the participant is now perceiving horizontal motion. Maybe the feedback signal can come from the horizontal tuned voxel from HMT plus, because it's a very motion sensitive area, and it was recently demonstrated that its activation of the 2 clusters, it actually correlates with the perception from Maren Schneider et al. So we were just thinking, okay, this columnar cluster will be activated, and probably we will send the feedback signal to maybe the homologous retinotopic cluster in. Or we make it a bit more complicated. It can also be that HMT plus is sending a feedback to the homologous clusters, the retinotopic cluster, because this needs to be enhanced. But also it can send another feedback or another signal to the other retinotopic cluster, to the vertical one in V1 to suppress it. So because we know from the anatomical structure that there are no lateral connections between the retinotopic cluster, they are very well separated. So somehow the other activity has to be suppressed, and we just want to test. So yeah, this is our result. So it's a bit of mixture. So I will guide you through it. So this is the row that indicates V1, and this is the row that indicates HMT plus. This is how the retinotopic cluster or the columnar cluster look like on an inflated surface for a subject. We did use all the physical motion run to obtain them, to obtain the 2 clusters as an extra, basically, localizer. And then we are asking, looking separately for each cluster, is the strength of the response of those clusters varying between the 2 conditions? So we have the physical condition and the ambiguous condition always on the x-axis, and then the y-axis we have the percent signal change. And what we see, and it also confirmed the previous literature, HMT clusters doesn't change their intensity of the response. It's basically the same. No matter if the stimulus is physical or the stimulus is ambiguous, the strength of the response is similar. Whereas HMT plus, that was somehow also expected. expected, when we go from the physical condition, very well separated, very well radiotopic organized, the ambiguous condition goes down. And it's very consistent across subject. This is a group result. It's just a standard deviation, very little, and across clusters. So this was also expected because if you think about the ambiguous condition as a feedback condition, then we do expect to have less signal. And then we ask, okay, this lower signal that comes and enter V1, is it specific to a specific layers? So we compute equivalent layers in our region of interest in V1 and FT. And here I'm showing you, again, differentiated per clusters, just to give a bit of confidence in the data, how the layer profile look like. So here we have always on the x-axis, the deep layers, middle, and the superficial. In solid line, we have the laminar profile for the physical condition, whereas in dotted line, the ambiguous condition. And when we designed the experiment, we thought that in the two conditions, we would have assumed that the vascular bias would have been the same. So then we could mitigate the draining vein effect by doing a subtraction between these two conditions and maybe enhance one layer that is more prone to a condition versus another one. What we did observe is that the shape is actually much more different than what we expect in the physical condition. So in a well-known feed-forward condition, we see the draining vein effect on top of a peak to the middle layers. But in the ambiguous condition, this is not there anymore. So we could do the subtraction. Some people still do it in the paper and then say that the layers that is changing the most is the superficial layers. So the layers that is changing the least, then it's the deep layer. But we are very careful with this interpretation because actually we didn't fully understand this curve here to begin with. Someone can also speculate that maybe there is not enough signal to begin with, so maybe all the layers are just flat. Or maybe the signal is so little and it has a different temporal dynamic at the neuronal scale that is not then being pulled with a normal hemodynamic response and then push it up to the superficial layers. But this is just some speculation. For the first time, we also look at the spatial organization of HMT plus that was not reported, and we could see that there are also no difference there. So HMT is really invariant between the two conditions from the strength of the response, but also from its laminar organization. So to check if there was really no signal in V1, then we try to go a bit deeper in understanding what those clusters were doing in terms of temporal dynamics. So we made use of the measures, the specificity that I introduced in the previous study to quantify how specific were those clusters. Okay, in the physical condition, super specific, as expected, because it's very well retinotopic organized. But this is how it's translated in event-related average. Well, the colored line indicates the response to the cluster to the preferred condition, and it goes up. And the black one, it indicates the response to the cluster to the not preferred condition, and it goes down. But when we go to the ambiguous condition, the situation is slightly different. The specificity is reduced. So those clusters are basically not preferring one more than another condition. And if you look into what generates this losing specificity, so the time course, we do see that there is a positive signal increase, even if it's low, but for both conditions, preferred and not preferred. And this would argue or collaborate a bit more, corroborate the second hypothesis we were mentioning, that there is a signal coming and the feedback will be a bit more global, reaching V1 and non-specific of the homolog clusters. HMT plus, again, maybe a bit boring, but it also keeps, as expected, its specificity. Though it's interesting to see the temporal dynamic as well, because while in the physical condition, we do see that both preferred and not preferred start, and they are like going a bit up. Then the not preferred one goes down much faster with respect to the preferred one. During the ambiguous condition, that there is a like the competition, if you want to think in terms of a mirror competition between the two classes, is a bit stronger, or that's what our data could support, because we see that they both stay up for a bit longer than our time, and then the not preferred one goes down. And also, like the fact that the temporal dynamics of V1, no matter which like condition is responding, is much more now synchronous with the one of HMT+. And this might indicate a higher coupling that is happening between the two areas, so potential feedback mechanism from HMT+ to V1. All right, so to wrap up here, we could see again with this ambiguous simulation, like the mesoscale, and how HMT+ and V1 react to that. We could confirm previous results related to HMT. It's very invariant, its response between the two conditions. But the novelty that we also bring here is related to the role of V1. And maybe that this, like we have a feedback signal that is more spread, more global, reaching V1. And one feedback to the homologous might be maybe excitatory feedback to enhance that visualization, and the other one may be inhibitory to repress out. But more experiment with a bit more improved maybe protocol would shed a stronger light of what we are observing here. Okay, so finally, I'm going to the last project where we even went a bit more deeper and we reached the macro scale. And our goal here was to a bit advancing our understanding of the mesoscopic underpinning of layer fMRI. So, and to do that, we did make use of two data sets. This is the first one. It's a post-mortem human brain data set that was published open access from people from Amsterdam, Harkemande and Pierre Bazin in 2022. And it's called the AHEAD. It's a very new and cool data set because from the microscopic perspective, usually people stain only one property. So you have a brain and you have the same staining across all the brain. This data set has an interleaved contrast mechanism. So they use 5 contrasts, one for each slide, and then they repeat it. But in the occipital cortex, where we were looking, they only have 3. And they stain a very high resolution, like 20 micron. And here I'm showing the original Nissen stain, silver stain, and parvalbumin. Nissen is a correlate of neuronal density. Silver might be seen as a correlate of fiber, so myelin in a bit more indirect way. And then parvalbumin that is a correlate of interneurons, so inhibitory neurons. They did a lot of effort to reconstruct all these slides and bring it back to a 3D model that it can be seen here. You can appreciate the slides at 200 micron. And then before cutting the brain, they put it inside a fMRI scanner, 7 Tesla, and they got some quantitative fMRI images at 400 micron as original resolution. And we are seeing here proton density, longitudinal relaxation, or transversal relaxation. So since this microscopy part and MRI were, well, almost aligned to each other, it could give us for the first time the possibility to look at individual area, multiple microscopic contrasts at the same time, and try to relate those in a very simple way with what we observe in the same specimen, the same brain with the MRI. And in particular, we will be focusing on R2-SAR. Okay, so the second part and second data set are data that we collect in Maastricht. So it's in vivo human brain, so living brain this time. And we use a recently developed sequence that we call multi-echo anatomical MRI at 0.35 isotropic millimeter resolution, and it's a whole brain. It basically leverages all the knowledge related to the API and the 3D acquisition together with the multi-shot. That this allows us to be fast and to have a good enough signal that it has already been demonstrated to be very similar to not having this approach, but much longer sequence acquisition. This work was done mainly by Farouk in our group. So, and say that we have at the end a 3 echo. So we could fit a mono exponential curve out of it, have an S0 value map, and a transversal relaxation beginner to start. And then we could also do the average of the echo and then just get an average. And from the same brain, we also get some racing state data with 7mm resolution, 0.8 from the same subject. And then we look at the time course. And in a very, very simple and dumb way, we did the average of the time course. And we use this average value to then plot it as a layer profile. Just a side note, this part of this dataset will be also publicly available and is actually a prolongation of the Kenshu dataset. So if you have like questions using the Kenshu dataset, you can even have like for free, like a higher anatomy and so on, and the rest. So these works that sounds maybe simple, it wasn't from the methodological perspective, because we had to overcome many artifacts that were for me new, but not new in the post-mortem field. And since we did want this effort, we tried to streamline as much as possible so that also other people can then make use of what we have done and maybe analyze different data following. For instance, the microscopy stain, since they were intervened, for the first time we also had like a problem of intensity regularization while taking together slides with the same contrast that they are not adjacent to each other. So, and we did some flick there and just fully automatized. Also, the microscopy people are very much aware about, if you want to look at the depth, that you need to be in an optimal position, like the angle between your local tissue orientation needs to be correctly aligned to the cutting side. And this was usually done by an experimenter looking at the slides and say, okay, this part we cannot consider for the laminar profile. And we try to automatize as much as possible. So now there is an algorithm that can indicate which area are good and which area needs to be masked out. And finally, also for the MRI part, since the blood is drained out and also the vessels themselves, there are some artifacts that are known in the literature as bubble. And then we streamline also this bubble detection. So that are basically this residual of the vessels that are very bright in T2 contrast and still will affect negatively the laminar profile, therefore we remove them. With respect to the analysis that have been done in the in vivo from the multi-echo MRI, these are all described in a more deeper way by the paper that is in preparation from Farouk Urban, and I just used that part. And the resting state, we didn't do any fancy processing. Then after this, so artifacts are hopefully masked out, we obtain our region of interest. As I said, I was interested in visual area, so we wanted to be 3 and HMT+. To do that, we use a cortex-based alignment approach. And with the target, we had like a functional visual atlas that unluckily was missing one hemisphere of HMT+. Therefore, we had to use another atlas that is a combination of multiple information, and therefore we macro-anatomically delineate our region of interest. Then we try to follow the natural structure of the data. So in postmortem, since there are slices, and the slices, yes, they are put together in a 3D model, but they are slices to begin with. Therefore, we did 2D segmentation, very careful. The only part that unfortunately we couldn't streamline and make it faster is the manual segmentation part that is there and has to be, and we are working on making them a bit better. And then we obtain 2D layers following again the equivalent principle. Whereas for the in vivo, since the data are 3D segmentation, manual segmentation, and then we get the layers out of it. Not to underestimate, it was also important to project back correctly our region of interest that were defined from the surface, and we couldn't use like the methods that were available online, so we had to make an effort there as well. Okay, finally, I'm going to the result of this last part. and showing you the laminar profile from the microscopy. So here on the x-axis, we have the cortical depth, we have the white matter and the CSF going to the right, the three contrasts that I was talking, so Bielatsky, correlate of neural density, theanine, correlate of myelin, parvalbumin, correlate of interneurons. And these are the four areas. So what we can observe to begin with is that these lines are not flat. So these value, these neuronal property are, as expected, changing across cortical layers, and they are changing in different ways. So if, for instance, we compute a correlation within each contrast across area to try to understand which contrast, because now we can look at three of them at the same time, is giving us more information to discriminate different area, we finally observed that beside Bielatsky and theanine that are known in the literature, also parvalbumin plays a role. So the distribution of interneurons is actually changing across cortical depth and changing across visual area, having a bit peaked, I would say, shaped for HMT task. This might be interesting to take into account also to interpret the result that we get from the layer fMRI field from a functional basis. Okay, then we compare the T2 star that we got from the ahead and the in vivo, and we look at the curves. Again, here, like one difference that we strike our mind is the profile being very different from middle towards surface between the head and in vivo. Well, it's surprising, but it also has an explanation. Like T2 star is becoming much higher in ahead in postmortem because there is no blood. There is only like one type of tissue property that is contributing to the T2 star decay, whereas in vivo, it became much flatter. So the co-localization of myelin and then the action of the iron in the blood make this profile being more flat, but still interesting to see that they change even across cortical area. And by now, it was only demonstrated that V1 and atrial gyrus A1 were changing across cortical depth, but not the other area. Okay, finally, we got to the last comparison. So to be as close as possible to the resting state fMRI profile, since the T2 star weighted signal, we got to our T2 star weighted, so the mean of the echo, and we plot it. So the shape is much similar to what we saw before, the quantitative T2 star. But it's interesting to see that this white line, dotted line, indicate like the horizontal line. And even with this simple way of computing a laminar profile for a resting state, we do see that there is a slight increase towards surface. And this increase is different from different area. Now the question comes again, why do we observe this increase? Is it only due to this draining band effect that is there even at resting state? Or maybe this comes from more the property of the tissue, so it's more vascular or is it more neural? This is the open question. And we hope that with this, I could show you that having this multi-contrast microscopy data set are really invaluable resources to study this structure to function coupling, and that it's also important to always think in a scale of what we can observe from the microscopy, but still it's postmortem, and what it changed when we have the living people, so with the blood inside. And with this, I want to thank my collaborators, especially Pierre-Louis Gazan and Farouk Kurban, and then Sebastian Dresbach, because all these projects start together during a year in the hackathon in OHPM, and then the remaining compartment of Maastricht team. Okay. So with this, I just would like to conclude with the final slide about future direction. So I hope I could convey that I'm really excited about layers, and I'm excited to try to understand better the signal, as many of you in this room. And then I kind of like the resting state approach, but I would like to combine it even more and more with these high resolution anatomical images and exploit the dynamic of the signal. Maybe we can identify some repetitive, I call it here in a simple way, laminar modes that if we partitionate a time course, we can find these repetitive modes of our response. And those modes, maybe now we have the chance to see if they come from the similar neural basis or maybe the similar vasculature basis, since now we can push in this high resolution anatomical information that can give us for each voxel if we are at least close to a vein, close to an artery, or within only tissue, even if it's not possible, but in the future. And on the other side, I'm also interested to trying to understand if with human fMRI, layer fMRI, we can get some information about local excitatory and inhibitory balance and the change of it, because this it has already been demonstrated to be very important in the clinical setting. But this is all based on electrophysiological invasive measures in humans. Maybe we get a chance to even image like non-invasively with layer fMRI. And to do that, maybe we should still go across case and even consult some experimental people, animal people that can shed a light having physiology, electrophysiology, and fMRI together. Okay, with that, I hope I didn't bore you so much, and thanks for the attention.
Any questions? Question. That slide physical motion versus humans. Yes. So I was interested, so part on C, but as you pointed out, you're seeing signal to be ambiguous in an area where there's no communication. So this is between these two.
Yes.
So my question is there really signal there? For example, did you compare that with the physical no motion condition? Or isn't it a perception of something falling in that's that second paragraph?
Okay, thanks for the question, first of all. If I understood you correctly, you are here asking if I would use a different baseline for the ambiguous condition, if I would still see a signal there. Is this correct?
Yeah, I mean, you have that's correct. You have the condition where you flash.
Yes, that I flashed the four of them. That's a good point.
So what does that mean?
Yes, so there is still a small activity occurring, and this was a pitfall or like a limitation of our experimental paradigm, because when you flash the four inducers at the same time in the frequent condition, actually the brightness of the stimulus is higher compared when you have the illusion, where only two of them they are presented on the screen at the same time, then they flash. So having the four of them and not being so much differentiate like apart from each other, it still induces a small signal that reflects the change in intensity. And we test that we could observe. But that was a good point. So in the future, I would suggest to remove the flickering as a control condition, because it's actually not helping us, but maybe has something that it also doesn't elicit a response just to the intensity.
Like just a black screen or something?
Yeah, just a gray screen. Yes. It will be a bit more keen.
Yeah, the people online cannot really understand the questions from the room. So for the next ones, maybe we need to repeat the questions. So I was actually very ambitious.
Yes. Yes, that's an excellent point, actually. Thanks a lot for bringing that. So the question was because when you look at the illusion, if you blink with your eyes, then you have the pressure. It can happen that you switch between the states. So then it's not anymore your brain switching by itself, but it's still sensory driven as you blink and then it changes. Since we did a lot of behavioral experiments before even starting going to the fMRI, we were aware of this problem. And we also were aware that people actually can use different strategies to keep being in a state longer, but that means that the mental strategy that they are occurring then is not anymore comparable across subjects. So in a way, shortly, we try to mitigate for that, giving to the participant very clean instruction. Try to not blink as much as possible. Like we let them understand that if they blink, it change. We try to keep it short, like 80 seconds is not so much. So if they got better in this, so that they could avoid to blink for that period, and then they were allowed to blink in the rest condition, because at some point it's physiological and we couldn't do more. And we try to really tell them to let the process be as natural as possible. So not think about, I had a participant who was thinking about going up to the steps to keep a perception on. That was screwing up the result. It was different. So yeah, we try to do it in this way.
One more quick question. Your longer index fibers. It seems like after longer check whether your index change.
So that's also another good point. Yes, the question was when I use the columnarity index, if I compute the columnarity index, if then the laminar value change across that. So this is a different question that can be still answered by our framework, by this third slide, but I didn't do it. Because our purpose was to see if the preference is the same, not the strength of it. The strength of it, we can embed it, and I did a descriptive part in the paper, a bit more extended, so that we can then relate to each voxel not only a columnarity index that is telling us just, okay, it's tuned or not without this intensity, but with sensitivity and specificity, we try to add this information, and that can play a role, and then try to change it, to complement in a way.
I was just curious about at the very end you're talking about. Was it clear the inhibition excitation balance? How your thoughts were pursued?
So the question now was to how I would do to basically try to test if local excitatory and inhibitory balance might change in humans. So it's still a very early idea, so I don't have a clear path, and I hope that through discussion I can develop it a bit further. But one thing that came in my mind was first to use this resting state and try to understand signal and dynamics, because maybe we have already some information there that is just not picking up at the moment. And if we can strengthen this by having an cross-species study, so if you have monkey electrophysiology, for instance, or some other animals, also fine, and have it laminar information, and if we can then perturb and see how this change in local excitation and inhibition will then be visible with the fMRI coupling, this will give us like a template of a shape that then we can try to see if that's like in a simple way can be found also in humans in a right way. Or another approach, maybe more challenging, would be to invite people, patients. This is it was like seeing already in epileptic patients. Yeah, if they can join, and maybe we can study the area surrounding the seizure and just see the resting state there, and maybe there if we can find like a different shape in the hemodynamic coupling or different like temporal signature that can be indicative of this change of balance. And I think I'm very interested in that because it has an advantage even when we study the functional fMRI by itself, because at the end this local, we always have like changes in local excitatory and inhibitory to respond to a task. Of course, when it breaks down and it goes over the threshold, then it became pathologic. But maybe we can even exploit that other part and see what is possible. I don't know more than that. Yeah, thanks.
Now we're 6 minutes over the time, so I think unless there are more questions, I thank everyone.